All right, good afternoon, everybody. I'm Jeff Glaser, the Laboratory Director for ALS's laboratory in Holland, Michigan. And today I'm going to talk to you about 1,4-dioxane, a little bit about the background with 1,4-dioxane as well as the analysis techniques that are available. So thank you all for joining me. And good afternoon to everybody and good morning to anybody out there on the West Coast. All right, quickly a little presentation outline here. We're going to talk about the background and chemical properties and uses of 1,4-dioxane, the health and environmental concerns that it presents, as well as the analytical methods and considerations that you might want to use when you're looking at setting up your projects. Just some quick chemical background on the compound. There are three possible structures of isomers of dioxane. There's 1,2, 1,3, and 1,4-dioxane, all depending on where the oxygen groups are located. However, 1,2 and 1,3 are very rare, so the focus is on 1,4-dioxane on this, and is really the environmental focus as well. There's some quick additional chemical background, the CAS number, the formula, molecular weights, pretty light molecule. Some additional names you might hear it called in addition to the 1,4-dioxane. There's 1,4-dioxycyclohexane, paradioxane, diethylene dioxide, and diethylene ether. Some additional properties. It is, as the last name indicated, it's a synthetic cyclic ether. It's a liquid. It's colorless. It's got a faint, pleasant odor. It's very flammable, and it can even form explosive peroxides just reacting with atmospheric nitrogen. So, a very interesting compound. Also has very moderate vapor pressure, pretty low boiling point, specific gravity right around 1, and the two properties that are really critical for it that make it an environmental problem for us. It's completely miscible in water, and it has a high mobility in soil and groundwater. There's several uses for 1,4-dioxane. The main one that really is out there is it's a solvent stabilizer for chlorinated solvents, including trichloroethane. It's used quite a bit in that. Also, it's a solvent for a variety of things, including impregnating cellulose acetate membrane filters. It's used in microscopy. It's formulations of inks and stains, coatings. It's also used in paints, lacquers, and varnish. It's used in the textile processes. It's pharmaceutical and organic chemical manufacturing, even impurities in antifreeze and aircraft de-icing fluids. So lots of uses for it out there, which is part of the problem. And then unfortunately, it's also found in a wide variety of household products, personal care products, and manufactured food additives, including cosmetics, cleaners and detergents, deodorants and shampoos, and I've got a picture of some of the things that you'll find it in. A lot of things I'm sure each of us have in our household on a daily basis. So it's very, very prevalent out there in the atmosphere and in the real world. As far as some of the health and environmental concerns, it's irritating to the eyes and the respiratory tract. It can cause things such as drowsiness, vertigo, headache, dizziness, anorexia even in certain cases. Also, it's got a very low acute toxicity. The lethal dose of 5.2 grams per kilogram in a rat. That's the oral dose. Additional information as far as the research goes on animals is chronic exposure shows liver and kidney damage. Also has caused dermatitis, eczema, drying and cracking of the skin, and some data shows potentially toxic to a developing fetus. The only real mortality data that we've got for humans is a 1978 study which there was dioxane-exposed workers, and it really showed no difference between the observed cancer deaths and the expected numbers. That's the good news. The bad news is it has been classified as a probable carcinogen by both the EPA, the International Agency for Research on Cancer, as well as several other organizations. It's also been known as a known animal carcinogen. So it definitely has got some properties there that we need to pay attention to. The inhalation route of exposure is the main one. It can also be through ingestion of contaminated foods and water or even skin contact, but that's usually minimal. Historically, it's not been evaluated in groundwater investigations as a target analyte. The low concentrations weren't able to be seen by the technology at the time, but it has been found in at least 31 of the EPA's National Priority List sites and likely present in many more. I'm sure there'll be some additional investigation on some sites that are still out there that where it has not been a target, where they've got new technology now they can see lower, and they'll probably find more. And then locally here in Michigan, it's really of high interest. Paul, who took over for Gelman Science, was a manufacturer of medical filters in the Ann Arbor area, contaminated a large aquifer in the area due to really poor disposal purposes or practices of the compound and some of the things they were manufacturing there. Yeah, one of the main things why it's such a important thing for the environmental community is it readily leaches into groundwater out of soil. It doesn't want to be retained in the soil. It's got low binding capacity. It's got very high water solubility. It doesn't biodegrade well at all. And because of that, the plumes that, for a spill, when there is a spill, the plumes tend to be larger and further down gradient than other associated solvents just due to the mobility of the 1,4-dioxane. Also, with the carcinogenic classification, along with the above characteristics, many states are now regulating 1,4-dioxane concentrations in groundwater at pretty low levels, and the EPA has also established drinking water health advisory and air and soil screening levels for it. So, you know, it's all good stuff, and I'm sure that we'll continue to hear more about this over time. The other issue with it is, you know, cleanup and treatment. It's not amenable to a lot of normal treatment technologies that are used for chlorinated solvents. Air stripping and activated carbon are ineffective in treating it. There have been a couple of effective treatment options for it, including advanced oxidation techniques. A couple of the ones that have been most effective is ozone combined with hydrogen peroxide, as well as UV combined with hydrogen peroxide or titanium dioxide. There's also been some studies done with membrane separation using reverse osmosis. And then under bench scale level studies, some different absorptive media combinations along with activated carbon, granule activated carbon, have shown some promise, but it probably will not work on a large scale. For the analysis, which is really what I wanted to talk about today, I just want to give some background on it. There's several techniques out there for the analysis. Most laboratories generally use one of two techniques for it. Historically, it's been either SW846 methods, A260 or A270. Unfortunately, both of these methods have some limitations relative to the both extraction efficiency, if you will, or purging efficiency, as well as the reporting limits. So a third option that's kind of been is really the more widely used one anymore is a isotopic dilution technique. And there's a couple different ways to do that as well. So I'm going to go through each one of these techniques a little bit here. It's typically run by GC mass spec, so that's gas chromatography mass spectrometry. The volatile compound, again, is volatile, it's A260. It's a semi-volatile, which is an extractable compound. It's done by A270. So first we'll look at A260 as a volatile compound. It's a mid-eluting compound. There's a whole list of volatiles, as you all know. Kind of comes out in the middle of the chromatogram. On the bad side, it does come out very poorly out of the water, so it has a poor, what we call purging efficiency. So we purge that sample with helium, and then it gets absorbed onto an absorbent trap. Both the purging efficiency is low, as well as the affinity for the trap, which is usually a charcoal-related material, is very low. So it doesn't do a good job getting it out of water and doesn't do a good job of trapping it. So therefore, the results from this are high detection limits or reporting limits and the possibility of a low bias in the result. This is just a quick copy of a MDL study, just kind of showing the performance of 1,4-dioxane compared to a couple other chlorinated solvents, if you will. You'll see on here the recoveries for the chlorinated solvents as well as the 1,4-dioxane are all showing around 100%, but the difference is if you look at the raw PQL number far over to the right, the chlorinated solvents are around 1 microgram per liter, where the 1,4-dioxane PQL in this case is around 120. We actually have gotten that lower now. We're probably doing somewhere around 20 micrograms per liter, but still much higher than the traditional performance of most of the chlorinated solvents that are out there. A270 is another technique that's out there and has been used widely. The problem with that is, again, with the compound, very water soluble, it doesn't extract well. It also may suffer some losses. It's very light compared to most semi-volatiles, so when you're doing the concentration step, that's prone to loss if you're not very careful. The internal standard that we use, each of these methods uses internal standards to do a relative response calculation. That's added after extraction, which is typical, but it's prior to the analysis, where some of the isotopic techniques I'll show you, it's a little bit different. And the problem with this is results in lower reporting limits, but with the possibility of a negative bias again in the results. So looking at the MDL study for that, it's down at the bottom again. In this particular one, the average percent recovery was 43%. Which isn't horrible compared to some of the semi-volatiles, but again, it is on the low side. Some of the normal things, some of the PNAs and some of those type of compounds typically are going to recover in water around 70–80% or more. So it kind of gives you an idea of the efficiency there. So a little bit of a trade-off. Sensitivity is better. We're down to 5 microgram per liter. Actually, we've gone down as low as 0.5 microgram per liter here at our laboratory. Successfully, and so big advantage over the standard A260 with that way, but you do give up something on the recovery side. Quick analytical considerations on the sample handling. The A260 method typically uses 40 ml vials. It's a HCl preserved vial. It's typical for volatiles. Standard 14-day hold time from collection to analysis. So nothing out of the norm there. And the same thing on the A270 side. It's generally a 1 liter sample. You can use a 40 ml vial if you've got some other injection techniques that are out there, but generally it's a 1 liter sample. It's non-preserved with a 7-day hold time. Now, the other way to do this is, in addition to the standard A270, A260, is with selective ion monitoring, or SIM as it's abbreviated. Again, we can do this both as a volatile and as a semi-volatile. It's just a different analysis technique with better sensitivity. And it's done by isotopic dilution. So what it does, it uses a deuterated isotope of 1,4-dioxane. That's 1,4-dioxane D8, used as the internal standard. And the thing that's different about this compared to the normal is that standard's added prior to any type of prep or analysis by the by the laboratory. So if you're purging it as a volatile, it's added prior. If you're extracting it as an extractable, it's also added prior. The extraction efficiency of the target and the deuterated compounds is constant when you do that, so they kind of cancel each other out. So if there's any poor purging or poor extraction techniques, those are kind of canceled out, if you will. And then we also recover, monitor an internal isotope to get the recovery outside of the two compounds, just make sure the recovery is good, and that's usually used, toluene D8 is the compound we use for that. Now, since the isotopic internal standard is added prior to the purging or extraction process, the extraction efficiency is constant throughout, and the amount of potential bias in the results is significantly reduced as a result. So those are all good things for that. Analyzing as a volatile by SIM, the use of SIM eliminates any interferences from other compounds. The purge and trap problems that you have are offset by the deuterated internal standard, and results in a lower detection limit and lower reporting limits with decreased potential for bias in the results. And again, looking at the MDL here for the waters, we're showing 2 microgram per liter here compared to 120 before, or 20. We can even go down as low as 1. Occasionally, maybe even a little bit lower. Recovery is good, 115%. Our PQL report typically is 1 on that. So. And that's what here in Michigan, that's the required reporting limit for 1,4-dioxane in water samples. There's also the extractable A270 method. Again, addition of the internal standard prior to extraction eliminates any potential bias during the extraction process. The method we typically use here in Holland is 3511, which is a micro extraction method. It eliminates any concentration step and possible analyte loss. Also allows for you to collect in a smaller sample size than a 1 liter. And the analytical results are parallel or consistent with those obtained by A260, in some cases even better. So some of our clients really prefer that technique. And looking at the method detection limit study on that, our concentration, although not nearly as low as the water samples, where we got a PQL of 5 and a percent recovery of 108%. So much better performance than the 43% than we saw. And 5 is a little bit higher than maybe you might think, but again, we're using a much smaller sample size than we are for the standard A270. And that's reflected here in the sample handling information. The A260 sim is basically the same exactly as the regular A260. It's a 40 ml vial, HCl preserved with a 14-day hold time. And the A270 sim with the micro extraction also uses a 40 ml vial, requires no preservative, and with a 7-day hold time. So certainly from a collection standpoint out in the field, the 40 ml vial is nice. If you're doing any kind of low flow sampling, it's great to collect only a 40 ml vial or a couple 40 ml vials compared to 2 1 liter ambers. Some concerns with the SIM analysis. You don't get any mass spectra, true mass spectra anyway. You're only monitoring individual ions, so you don't have a absolute 100% confirmation of what's there. It's pretty reliable, but there is a potential for misidentification. For the micro extraction, the way that's done, there is a potential for a hold time exceedance, particularly if the samples have been held onto in the field at all. If the upper quantitation limit is exceeded, the sample must be re-extracted. That can result in out-of-hold data and requirement of an H flag, or could cause, if you held onto it, we might need to charge rush cost to get that turned around quicker and extracted quicker. There is a longer hold time available by method 522, which is a bit of a newer method compared to certainly newer than the A260 and A270, which will allow a 28-day hold time. However, the preservation is much more involved. There's no preservation for the A270, so it needs preserved before it goes out in the field, and again once it's in the field, and it may or may not be accepted by the regulatory community depending on where you're sampling at. And just a little bit on the EPA 522. It's a drinking water method. 1,4-dioxane has been identified as an emerging contaminant in drinking water. It just got done being evaluated for the unregulated contaminant monitoring rule, the 3rd generation of that. Every so often they look at certain things that potentially could be in drinking water supply, in municipal drinking water systems, and that was one of those. It has significantly lower detection limits down in the part per trillion, roughly 0.04 part per trillion, or excuse me, 0.04 ppb, so 40 part per trillion. It uses a 500 ml sample. It is preserved. It increases that holding time to 28 days. It's done using a solid phase extraction, different than a liquid-liquid extraction using cartridges. And again, the analysis is done by isotopic dilution with a selective ion monitoring method. So it's kind of a hybrid volatile and semi-volatile method. It's extracted like a semi-volatile. However, when you do the analysis, you use a tune evaluation using the volatile tuning compound BFB, and also uses a volatile analytical column just to get a little bit better response out of it. All right, so quick summary of this. Certainly due to its chemical characteristics, regulation of 1,4-dioxane will probably become more stringent in the future. Treatment and cleanup are difficult just because of its chemical properties and the way it moves through the water and soil. It can be treated either as a volatile or semi-volatile compound with several analytical approaches available. And the decision as which one should be used is based on project, your DQOs of your project and or the site history. If you have high concentrations, you might tend toward A260. If you have low concentrations, you want to go one of the other ways, ideally one of the SIM methods as well. So, and 522 may be an option down the road. We've seen more requests for that in the past couple of years, and I think you'll probably see more as they try to push the limits, detection limits of the compound. So it's the other things I got here is the GCMS analysis by full scan can better handle unknown samples and unknown concentrations. However, the high reporting limits or negative bias should be expected and factored into the decision making. The SIM provides the most accurate analytical results. It's best suited for known concentrations or low-level monitoring. And then the SIM holds increased potential for hold time variances with the preserved sample, but certainly places a greater burden on the sampling crew to get that right, and also requires regulatory buy-in. So prior to using that. Got some references there. If anybody's interested, I can certainly get those for you. There's a number of reference documents out there online that you can find regarding the uses, the treatment, the analysis, and some comparative studies as well that are all out there. So if you're certainly interested, there's a wealth of information on the web for you out there. And that's pretty much my presentation today. There will be a recording of it posted on our website, and we'll send out a link to all the participants on this. But certainly, I thank you for attending, and I'm available for questions if anybody has any. It looks like I do have one. It says, can't you use 1,4-dioxane as an internal standard and surrogate by A260 SIM rather than toluene D8? We do use it as an internal standard, but we still want to monitor the recovery using the surrogate, so we actually use both. So 1,4-dioxane D8 is the internal, and the surrogate's toluene D8. Another question is, are there any semi-volatile extraction methods that should not be used or less efficient for 1,4-dioxane? There's three different techniques out there that I mentioned, right? There's the standard 3510 separatory funnel extraction. It can also be done potentially by continuous liquid-liquid, which is 3520. I don't have any data on that. From what I've talked with our technical director, they used to do it that way, and it probably is a little more efficient than the 3510. 3510 is probably the one you really need to watch out the most, just because of the volatility of the compound. If your water bath, when you're concentrating it down, is too hot, you're going to lose it, and recoveries will be low. With good proper technique, you can get up to 60 to 70% recovery in, say, your laboratory control samples, but without that, it can drop down in a hurry. And let's see, I think those are the only questions I've got currently, unless anybody has any more. I'm certainly available for more if anybody has any. If not, I certainly do appreciate everybody attending today. I think it's an interesting compound. It certainly presents challenges for you guys as engineers and clients of ours out there on how to treat it and handle it. For the laboratory, it presents some challenges as well. Really requires good analyst and good technique in the laboratory. So you definitely can have a wide variability between results between laboratories. So I do know that you want to make sure you have whatever technique you're using. If you're a laboratory that's listening to this, or you're using another laboratory, they've got the data to back up the technique. Looks like there is an additional question. Do we know if certification or accreditation will be available for A270C? That is available and out there. It's actually listed now on the target compound list for A270 for the CLP, most recent CLP contract laboratory contract laboratory program list, and there is certification available through NELAC and probably some of your states as well. All right. Well, if anybody has any questions, you feel free to email me directly. My email is on the page here, and more than happy to talk to anybody individually about any questions or additional concerns you might have regarding 1,4-dioxane, and I thank you for attending today.